Today we're going to practice graphing absolute value equations and inequalities. We are specifically going to focus on using a table of values. Once we get familiar with using a table of values and we start to see the patterns that form, then it might not be necessary, but to start out and to see what an absolute value equation should look like, we're going to start there. So our first example is y equals absolute value of x. It's the most basic absolute value equation. It's similar to if we had y equals x, right? It's the most basic version of slope-intercept form. It would be going through the origin with a rise of 1 over 1. Then, once we mastered our parent function, we were able to add y-intercepts. We did different things with our slopes. So we learned with our parent function and we went from there. We're going to do the same thing here. So using a table of values, we're going to see what happens with our parent function. What does the original function look like? So we're going to plug in 5 values. 2 negative, 1 0, and 2 positive. So they could be arbitrary. I'll pick -4, -2, 0, 1, and 5. And we substitute the value into the equation. So I'm going to do the absolute value of 4, the absolute value of -2, the absolute value of 0, the absolute value of 1, and the absolute value of 5. Well, the absolute value of 4 is +4. Absolute value of -2 is 2. 0 is 0. Absolute value of 1 is 1. Absolute value of 5 is 5. And from this, we have ordered pairs. So I have a -4, 4. I have -2, 2. I have 0, 0. I have 1, 1. And I have 5, 5. And I would get the exact same looking shape if I had plugged in any other points. The absolute value graph does take the shape of a V. So our parent function looks like a V. Some things that we should notice about the parent function is that it originates at the origin. Right? It also is completely positive. There's no way we can get a negative value for our output, because if we're continuing to take absolute values, we're never going to get a negative value. So that's why we have all positive values and then it pops back up positive again. So all positive outputs or a range. And then we also notice that our lines, which are going away from the origin, have a slope of 1 over 1. And then the opposite side obviously has a slope of -1. So it's either a slope of 1 or -1, depending on which side of the V we are focusing on. But it's the most basic, and again we call this the parent function. It's based at the origin. Everything is positive, and we have the slope of 1 or -1 as we go out from the origin. So now we take the same concept and we're going to transform it. So when we start adding things in, we start subtracting things, now our parent function gets transformed. We're also in this example going to throw in this idea of an inequality instead of just an equation. So again, using our table of values, we are going to find 5 points that we can plot on our graph to give us some sort of idea of what this graph looks like. So I'll do -4, -2, 0, 2, and 4. So I substitute x minus 4. No. -4 minus 2, absolute value -1. -2 minus 2, absolute value -1. 0 minus, these are plus, my bad, plus 2 minus 1, 2 plus 2 minus 1, and 4 plus 2 minus 1. So we simplify our absolute value. This is going to be the absolute value of negative 2, which is 2 minus 1. 2 minus 1 is 1. Here we're going to have 0. 0 minus 1. We get negative 1. Here we're going to have 2 minus 1 is 1. Here we're going to have 2 plus 2 is 4. Minus 1 is 3. Here we're going to have 4 plus 2 is 6. Minus 1 is 5. So let's plot our ordered pairs and see what our transformation looks like. I have a negative 4, positive 1, a negative 2, negative 1, a 0, positive 1, a 2, positive 3, and a 4, positive 5. Now, it looks a little different. There are a few things we need to notice. If I'm going to draw my lines in, due to the fact that this is an inequality, I need to have my lines represent the inequality. So with this symbol of less than and not less than or equal to, when I draw my lines, I want to have dotted lines to represent that this is an inequality that I don't want to include the points on the line. So in the same way I did with my linear inequalities, I'm going to do with my absolute value inequalities. So the dotted line is due to the fact that I have the less than sign. Now, we noticed in the parent function that it was originated at the origin, right? And here we don't have that. We also noticed that in the parent function all the values were positive, and we see here that we have a negative, right? Now, is this something that is possible, or did we make a mistake? Well, if we look at our function, we have additional work outside of the absolute value function. So if we were to only have absolute values, then all of our responses would have to be positive. But since we are doing extra subtraction after the absolute value, it is feasible for us to come up with a negative number. So that's okay. And the other thing we noticed was that we have a slope of 1 over 1. And in this case, we are still noticing our positive 1 slope and our positive negative slope. But that might not always be the case, depending on the function. So this is what we call a transformation, or it's part of the family of absolute value functions, the parent function being the original, and then all of the family members are the various transformations. Now, the last thing we need to do in an absolute value absolute value inequality is a test point. Same as we did before, we want to test and see where are our solutions. Are all of our solutions going to be below the V, or are all of the solutions going to be above the V? So the easiest test point is going to be our 0, 0. So let's test it in. 0 is less than absolute value of 0 plus 2 minus 1. Absolute value of 0 plus 2 is 2. Absolute value of 2 is 2 minus 1 minus 1. 2 minus 1 is 1. Is 0 less than 1? Yes, this is true. So we want to include all of the values below our V and not include the values above the V. And in the same way, when we had our absolute value equations and our linear inequalities, the points on a dotted line are not part of the solution set, but everything in the green is. If we were to have a solid line, then the points on the solid line would count as part of the solution set. So to practice, I want you guys to do a self-check. Come in with the next problem completed in your notes so that we can discuss and maybe answer any questions that you have. So I want you to graph the following linear inequality, absolute value inequality. My y is going to be greater than or equal to negative 1/2 absolute value x plus 3 with nothing afterwards. So using a table of values, testing 5 points. You can do a quick sketch in your notes, make it as accurate as possible. Don't forget to do your test point and shade. And we will discuss your answers tomorrow.